All right, my friends, here we are, lecture 4. We're going to return to logic. We started with logic and did so using Jaynes. We're going to use only a little portion of Jaynes today and finish up with my chapter 3 in the book Uncertainty. And after that, we'll be done with logic, at least in the introductory sense. The point of all this was, the point of all these first 4 lectures, and the point of one more to come, there's going to be one more to come after this, is to prove to you that uncertainty and certainty are all derived not in ways that we think. Not all beliefs that we have are empirical. Not all are observational. Empiricism is false, as we'll see today when we return to logic. Logic cannot be the epitome of all thought, as rationalists tell us. That's the one thing I've been trying to hammer home. And this has a lot to do with how we eventually interpret models, how we use mathematics to interpret reality and all this kind of a thing. We need to understand the limitations. That's what I'm really trying to get us through here. The limitations of the way we think of things. And to not fall prey to, in the end, we'll see, they say, follow the science, follow the science. What does that mean? Well, we're going to find out exactly what that means as we get to it, but we don't want to fall prey to these kinds of things. We're going to see exactly what all of this means and really think hard about the origins of everything. We need a really firm foundation before we can move on and do any of the math. So this week we'll finish up on logic. And then next week, which leads into the next topic, which is going to be induction and the various forms of induction there are and so forth. And after that, we'll be done. And then finally, in 2 weeks from today, we're going to be doing probability. We'll start with, we'll go back and return to Jaynes's book on his probability robot, where he wants to have a robot that can decide uncertain propositions, and can these be numerical propositions and so forth. And we're going to build that robot as Cox did, step by step, and that leads us to probability. And then from probability, then we're already going to be in the math at that point, but we're really going to get into the math after that. All right. So the very little bit that we're going to take from Jaynes today is just simple Boolean algebra. I'm not going to do it. I think all of us probably who are watching this video know Boolean algebra, and if not, I think it's extremely intuitive, so I'm not going to belabor it in any sense. We're dealing with propositions here. We've been dealing with propositions the whole time. That's what we're going to continue to deal with. Even mathematics is going to turn out to be nothing but propositions. So we need to really understand propositions. We've been using these capital Latin letters to describe propositions. So we have a proposition A. When we see it here, when we write it just like this in formula form, and this brings us to notation. When we write it in formula form, we take this to mean A is true, or we're assuming A is true. And so in Boolean algebra, you might have 2 propositions A and B. And we read this as A is true or B is true. The entire phrase inside quotation marks. Those quotation marks won't usually be there in the notation. This is a problem if we don't remember that they're there. This is the problem of notation. We're going to get into this. Notation can be a great facilitator. It can make equations so much easier to prove and to use and manipulate and all this kind of a thing, and it's wonderful. But it also leads to the deadly sin of reification. The equations, like I've said many times, they become alive. They become realer than reality. And we're going to learn today that that can lead us into error. So equations are always stand-ins for our thoughts, for things we're trying to say about the world. All right, so we got to be very careful about this. Well, not in this. This is very simple, but we're not talking about individual propositions in this. We're talking about this joint proposition. So when we forget that those quotation marks are there, because it's just too cumbersome to keep writing those kinds of things, we can run into trouble. Now, I think all of Boolean algebra is very simple. We're not going to use a great deal of it anyway. There's nothing that's beyond. Uh, here, this means A and B. A and B. When you don't put anything in between A and B, well, that's very simple. We'll use this over and over and over again. We don't really need to get too much into this. You could read it in the second chapter of Jaynes, and no problem. The only one that sometimes gets people is this entailment. This if A then B thing. All this means is the logical Boolean. The Boolean equation, the way to write it, this is one way of writing it, and this is another way of writing it. All this means when you see this kind of a thing, it doesn't mean that we can deduce B from A. It doesn't mean that at all. All it means is that the equation A means A is true means A and B are true together, simultaneously. The statement A and B is itself true. And so sometimes this throws people for a loop, especially when you look up truth tables and the like, and it doesn't make quite sense the first time. For some people, have a hard time following it. But this is just one form of the notation. This is another. Jaynes introduces both of these, and I prefer this one because it's a lot simpler, but until you really get going, and then this one becomes a little bit easier as we go along. However, it's just notation. And notation can be a bear. So for instance, I started off in physics. And the older physicists will have, now if those of you who understand integration and everything will get this. Maybe if you haven't seen integration before, this will be hard to follow. But some of these old school guys, and still in some physics things, they'll write integrals like this. Whereas I prefer something like this. Both of these are this is the integration symbol, such as it is in my handwriting. This is the thing that we're integrating with respect to the variable x. And here is the thing in the old-fashioned way that we're integrating. It's outside of this this dx here. There's nothing wrong with this writing. It's just a style. It's a style that some people prefer. But in my mind, sometimes I'm putting parentheses around this equation. Well, this just comes out to be a constant, as everybody knows, if you've seen integration, multiplied by some function. Here, it's very explicit that it's inside this integration thing. We're integrating this whole thing with respect to it. It's just, again, it's a weakness of the limitation. It's a weakness of the notation. It's neither one is wrong. Neither one is right. They're just ways of scratching on the board the ideas we have in our heads. We always got to keep this in mind. So you'll come across all these kinds of things. And the one that's really difficult is not. So there's lots of ways to write this. A is true. We want to say A is false or not A. Well, we could write not A. That's very simple, not A. And that means it is not true that A is true. Or we could write, I think Jaynes uses a bar over the top, and that means not A. Well, in statistics, as we get into statistics, that bar has a different meaning. So we would confuse the statistics meaning, which means taking an average of, a numerical average, with this meaning not A is true, or rather A is false. Some people will put a complement over there, or a C rather, and mean that A is false. But that can mean the complement of a set, so that's confusing. And some people will write a little a logic symbol that means not. It's the same as the English word not, but in a logical term. That's perfectly fine. Some people will write a prime, but that can mean a derivative. So all of this notation, none of it's. It depends on which book you're using, depends on which source you're quoting, and all this kind of a thing. So notation can be very tricky, and the notation is not the important part. Like I said, once you learn a notation, you can just start flying with the equations and so forth once you get good at them and everything. But we're going to learn real shortly here that we can't necessarily apply all those equations. So we're finally going to apply some equations to some real life logical equations to some real life things here. and see what could happen when we do so blindly, or a notation. Now, we're going to use David Stove here today. We're going back to this book. This is just a treasure. Most people don't know this book. In probability and so forth. The entire first half of the book is all about induction, and we'll do that. We'll do that next week. This is why am I wearing this today? Well, it's bitterly cold in the end of April, and someone said I could be like the Carl Sagan of probability. So I went and found my Carl Sagan jacket. I got this at a thrift store for $1. Had a pair of glasses in the pocket too for reading, which I lost. Anyway, so my point is logic. Logic from David Stove. This first half of the book is all about induction. But the second half, he could have entitled this whole book Logical Probability. The second half of the book is all about logical probability and is in perfect accord with Jaynes, but on the more philosophical side of things. So what we're going to do today is prove to you that deductive logic is not empirical. So this rationalist, again, they say this is the height of all thinking is logical thinking and so forth, but it's not. And logic cannot be empirical. The truths of logic we cannot learn empirically. There has to be something more. Our form of thinking cannot just be from observations. There has to be a way that we're going to extrapolate from individual instances we see to these universals, and that applies to logic too. Not only is logic not empirical, it is also not formal, so we need to be careful with our equations. Okay, so the first thing is we'll do the not empirical. I'm now going to follow out of my book. I have some very simple examples to try to distill all of Jaynes. We can see things like this. Let me write up the equation here, and then we'll work on it. Let me make it even shorter, just for the sake of board space. Okay, J and H are real names, real people. James is a man and Harry is a man. Entails, this is the entailment bar, the conclusion bar. This is a symbol to mean entails. It's a logical argument I'm making here. James is a man and Harry is a man. Entails, James is a man. Nobody would disagree, I hope. But we do not see the entailment. We can witness that James is a man. We can witness that Harry is a man. And we can certainly, again, witness the conclusion, but we do not see the entailment. The entailment is not something that is in observationally. It is not something that we observe. It is something that we induce. It is something that we pick up. That's obvious enough. Now, from these individual sorts of things that we learn, sometimes we can learn. The whole point of this is the entailment itself is something we have to see. If you can't bring somebody to see this entailment, this logical entailment, not everybody can see every logical truth. Okay, not everybody can follow every equation. It doesn't mean that because this is logical knowledge that everybody can grasp it. They can certainly grasp this and this, for instance, and the conclusion, but it doesn't necessarily mean they follow the logic of this kind of a thing. Now, we can form schemas of all this, and we need to be careful about that. So we could just say, as opposed to J and H, we could say this. We could say X is M and Y is M entails X is M. Now that's a formula. This is a logical formula. X is M and Y is M entails X is M. We did not learn the truth of that previous entailment because this equation is true, or seems to be true. It is true for some instances of X, M, and Y. But now we're going to understand. Now we're going to move to. That is to say, so you go to a textbook and you're in the standard way of learning these kinds of things. They have you proving these theorems or proving these simple things, or they write down the equations. They say, let's use it for this. Okay, you do that. But it's not because this equation is true that because James is a man and Harry is a man, therefore it entails James is a man. It's because they're men and James is also a man. That's because of the essence of the things, not because of the equation. The equation is not making things true. The equation is not is describing our thoughts about reality. It is not describing reality itself. It's describing our thoughts about reality. So let's move to something much more subtle and difficult. So we're going to do, I'm going to try to prove to you, it's not so easy to follow this. I'm going to try to prove to you that logic is not empirical, okay? Well, we just had a slight proof there, very, very minor proof that entailment is something that we get, a logical sense that we get from individual instances of that schema that we observe, and then we extrapolate through our intuitions, through a form of induction, to come to that knowledge of that entailment. All right, so we don't use logic to get to that. We can't use logic. We have to have, either this stuff has to be inbuilt, or we have to have extrapolated that and used induction. Everything is going to turn out to be reliant on induction. Okay. So let me, I'm going to follow Stove here. I have this in my book too. The notation is slightly notation again. The notation is always slightly different. So let me write this up. This is a very common logical schema called Barbara. They gave these names from back in Aristotle's days. So we have X is F, and all F R G entails X is G for all X, all F, all G. Okay, that's just a logical scheme. And the example he gives, and I'll write this down too. So X is going to have some predicate, and all F or G entails, did I write this correctly here? X is G for all X, all F, and all G. Okay. Now, we can see things like this. We could have this. We could say Abe is in room and all are bald entails Abe is bald. Okay. So this is an individual instance of a schema like this. Abe is in the room, and everybody in the room is bald. Entails, the logical entailment, Abe is bald. That's the logical judgment, the logical formula. Well, that's an instance of this right here. So do we learn these things empirically? No, we don't. Just like we couldn't learn the entailment empirically, we don't learn this empirically. We learn individual instances. We don't even learn this entailment again. All we can really see is things like this. We can see Abe is in the room and all are bald. And Abe is bald. That's what we see. That's our observation. This is our data point, if you like. We have this data point right here from which we extrapolate that first entailment, that logical entailment, and when we meet other instances of things like this, we form this rule up here. We form this rule up here. But It's not an empirical judgment. It has to be an inductive judgment because we don't learn these sorts of things empirically. And the reason is it's a very lovely argument. I adore this argument. We have to know somehow that this confirms this. Okay? We could learn that this confirms this. Just as we just said, this particular thing is an instance of a schema like this, what that entails in there. But in order to know that this confirms this, we have to know something about this confirmation. We have to have the pre-logical knowledge about what confirms even means. So we must have had in mind, if logic is empirical, a statement such as whatever this statement is going to be. I think I write it out as Stove writes it out as an equation called O1. An observation statement. There must be some observation statement in the world that if we learn our truths of logic using observation empirically, there must be some observation statement that teaches us about this confirms. It's going to be obvious to you, yeah, this is confirming it. But we're talking about confirms. We're talking about the logical knowledge confirms. What does it mean? We all grasp it because it's so simple, I think, for most of us, that it's so easy to see that we don't see that jump, that intuitive jump to say we're confirming something is itself not something that we learn by observation. We could say that there's some observation statement out there that brings us to this, but then there must be the judgment that this observation statement confirms this confirmation. If we say that logic is empirical, if we say we've learned every one of these things empirically and all we're doing is just connecting the dots from our observations and logically tying them together. No, it's not like that. We must have this idea of what confirmation means induced through some form of intellection that is not deductive logic. Because we don't get that confirms. We can see that this matches this, but to see that it entails it or confirms it, that's an entirely different thing. That proof, and there could be some observation statement that we use to get this confirms, but then we'd have to have another observation statement that confirms this, that confirms this, that confirms this. It just goes in a vicious circle. In the end, we have to build everything on induction. Now, if that's not entirely clear, it's because it's a very subtle point that a lot of people that can miss. They're so intent are they just to get to the equations and so forth. Well, I urge you to think about that entails and confirms the idea that we have this logical knowledge. Aha, it does in fact that X is M and Y is M entails X is M. It's that entails, the entails, the confirms. It's that logical judgment that we're making. It's a true one, but it's not found itself using deductive logic. It has to come from somewhere else, and that's the whole point of this book, the ground of induction, the rationality of induction. Okay. All right. So now, that's going to be a lot to think about. It will be easier to think about this next week when I bring up, if it all doesn't sort of click for you yet, you have to go back and read Stove. I'll put the stuff in the lecture notes. You can read my chapter 3, I think it is, 2, rather. Chapter 2 in my book. I'll have excerpts on the blog. And I got to get the chalk. Now, what we want to be able to do is to show not only that logic is not empirical, but logic is not formal. All right? Logic is not formal. Math is not formal. And what do I mean by that? So what does Stove mean by that? Let me read you this. A formality of a logical argument is when, I'm quoting now, it employs at least one individual variable, or a predicate variable, or a propositional variable, and places no restrictions on the values the variable can take. It's that no restrictions. So that means, again, I've warned us time and time again, when we write down an equation and we say it fits in the world, everywhere it's used, that may or may not be true. And I'm going to give you some good examples of it right now, and especially in logic. So logic is applicable to the world, no question about it, but we have to restrict either the predicates or the proposition or something like this. Okay, here is a logical proposition. Let me write it up. Let's see here. This whole thing is Logic 101. You take an ordinary logic course, they're going to show you something like this. We're going to say, if it is true that if P then Q entails, if not Q, then not P. It's just a standard logic. Let me give you an example first where it works. Make sure I don't get this backwards. And then I'm going to give you an example where it doesn't work. And this example is the favorite of some people. Let's just, I don't know if anybody wants me to call them out or anything on this particular lecture, but here we go. So let me do this. Let's walk through this to see it can work. This is a perfectly true logical thing. And if logic was formal, this should work for all P and all Q. Right? Well, it doesn't. But it works for this. If there's food, then I can eat. That's what Q means. I can eat. And P is there is food. I'm not going to write the whole thing out. I have the whole example written in all its glory in the book. But here I'll tell you. Okay, if there's food, I can eat. And this works. If there's I can't eat, not eat, if not eat, then no food. Okay, that means if I can't eat because there's no food. So this works. This logic works absolutely fine. But it doesn't work for every possible P and Q that we could stick in there. Logic is not formal. We have to place restrictions on this equation, which are always there in our minds, but they're not necessarily there in the equations. And when we get into this, especially when we get into abuses and statistical models and probability models of all kinds, there's always a host of implicit premises. Remember, we started off in our first lecture with implicit premises that people have in these arguments and so forth that they forget are there. And because the notation is so easy to use, they just blaze away with the notation, forgetting about all the implicit premises which constrain these type of things and make them far less restricted than we want them to be. Okay, let me just give you this. And then I want you to find, I'll show you the homework in a second. Let me change that. Whoops, I'll leave that one up. I'm going to give you an example where it doesn't work. This is a very humorous example. This is also from David Stove. It's one of my favorites. Baby cries is our proposition P, and Q, we beat him. All right? So if baby cries, then we beat him. Okay, that one works. But does it work the other way around? Logic says it must, because if P then Q entails, here's that entails again, if not Q, then not P. In this case, it means we don't beat him, then he doesn't cry. not Q. We don't beat him. Baby cries, not P means doesn't cry. So if we don't beat the baby doesn't cry. Well, that's false, in fact, in real life, right? Babies cry for all kinds of reasons. So this is his baby cries, baby beat example. He gives many more in this book, in the Rationality of Induction book. Lots and lots more details and everything like this. And maybe if there's more interest in everything, we can go deeper into that. And eventually, I think we will, because maybe I'll have some other lectures that are sort of adjacent to the class or not part of the class, but can be used as background information to the class to show deeper insight into where objections to induction come from, like David Hume's induction skepticism and so forth. Well, we're going to cover a little bit of that, but I'm not going to show the proofs. He's got several books. I think it's in this one right here too. Yes, it's in Anything Goes. It's also called Popper and After. This book has 3 separate titles, and this is one of them. This is a good one to get. It shows exactly where skepticism in induction arises, which we'll talk about next week and all this kind of a thing. So your homework for today, for this week, is we have this perfectly good logical equation up here, but it doesn't work. We have to constrain it. I want you to find your own P and Q where it works and where it doesn't. All right, so I gave you an example where it works, and I gave you an example where it doesn't work. And that's your homework, to find one where it works and to find one where it doesn't work. I'll also write this out on the blog in case you forget or something like that. All right, that's it for this week. Next week, we handle induction and intuition. And then I promise you, we'll start to move to the glorious math that everybody's waiting for when we introduce Cox theorems for the proof of that probability can be quantitative, and it turns out to be a function between 0 and 1. Thanks for watching. Thanks for listening.